Advanced Math Lesson 65, radicals in trigonometric equations, and then graphs of logarithmic functions. So, radicals in trig equations. The only ones that really matter are radicals that cover your trigonometric functions. So we'll do two examples here. This first one we'll do sine of x minus square root of 1 minus sine squared of x equals 0. Now this other equation is going to be tangent of x minus square root of 3 times sine of x plus 1. That's going to equal 0 as well. So there's a couple of different ways we can solve these, but the first thing to notice is that this equation, the radical covers the trigonometric identity. In this one, the radical does not. So the thing to take away from here, this equation, easy to solve because the radical doesn't cover the trig identity, and we know that root 3 is already a number in our reference triangle, so we're not going to have to use anything weird with our trig identities. However, on this one, the radical covers sine squared of x. So I'm going to have to do some work here to get that out from underneath the radical. And there's two options here. I'll show you the first option, which is easier, and then we'll go to the second option because why not? Now the first option, which is easier, go ahead and separate the radical to one side, something we already know. So we'll have sine of x is going to equal square root of 1 minus sine squared of x. Now from here, we're going to square both sides of the equation. All right. When we do that, what we get on the left is sine squared of x. On the right, we get 1 minus sine squared of x. Now, what they're going to do is they're going to set the equation equal to 0 again. Or actually, you know what? Let's not do what they're going to do. Let's do what I'm going to do. All right, so yeah, I said I was going to do the easy version first anyway. All right, so let's go ahead and move all the signs to the other side. That cancels. Sine squared of x plus sine squared of x, like term, so I get 2 times sine squared of x. That's going to equal positive 1. From here, since the 2 isn't interfering with the trig identity, I'll go ahead and divide by 2. So sine squared of x is going to equal 1/2. Now, the last thing I can do here, and this is the easier method, I'll just square root both sides. So what happens here is instead of sine squared of x, I just get sine of x, and that's going to equal the square root of 1, which is 1, over the square root of 2. Now this denominator is irrational, but I have to perform a trig function anyway, so I could rationalize it, or I could look at this and say, you know what, it's an irrational function, or it's a trig function anyway. Let's find out what triangle this makes. So if I do sine of x, and sine is equal to opposite over hypotenuse, then I've got a hypotenuse of root 2, and I've got an opposite side of 1. What reference triangle is this? Well, that's the 45-45. So x is going to be 45 degrees. Right? And then I think about my reference or my unit circle, and I ask, hey, where is the 45 degree? Where is sine positive at a 45 degree angle? I know that is only the first and second quadrant. The 45 degree angle of the second quadrant is 135 degrees, and that's my answer. Okay. Now, the other way that the book would like to do this is at this point, they would take this equation to sine squared of x. So again, I'm starting from up here, and they would set it equal to 0 again. So they'd have 2 sine squared of x equals 1. They would subtract 1 from each side. Then they would have 2 sine squared of x minus 1 equals 0. From here, they would want to factor and use the zero factor theorem. Well, you can't use zero factor theorem. Well, you can't perfectly factor the square because you'd have a lead term of square root of 2 of both the sine and x's. So what they do here is they go ahead and they divide everything by 2 preemptively. And so then what they get is sine square root of x minus 1/2 is equal to 0. From there, the book suggests then we can use a difference of two squares, and they would factor sine squared of x minus 1/2 into sine of x minus 1 over root 2, and then sine of x plus 1 over root 2 equals 0. From here, a zero factor theorem would give them an answer, plus minus 1 over root 2. Whoops, that's a 3. All right. Now, the difference between this and the answer that I got is my answer up here just gave me sine of x is 1 over root 2. Now, this one has plus or minus. The reason why I don't like this method is because the problem when you square trig functions sometimes is that instead of having a loss of answers, you get a gaining of answers that aren't possible because like up here when we did our unit circle, we were looking for where sine is only positive, right? So we're only looking for positive answer values, but here, once they did the difference of two squares, they now have positive and negative answers. That's just one of the things what happens when you find the square root of a number. Your square root is going to be positive or negative, and you're not sure which one it's supposed to be. So they're going to end up with all four 45-degree angles. Their answer is 45, 135, 225, and 315. And their solution is to use your calculator in process of elimination to figure out which one of these four answers are correct, and they find out that these two were not correct. That seems a little bit convoluted to me when we've already got some good algebra rules up here that will give us the correct answer. And as far as I know, all the rules I use in this don't violate inviolability of trig statements, and they haven't broken anything for me yet. So I'm going to recommend you use this one. Now, the reason why I show you all this work down here and the difference of squares and the zero factor theorem is because that's what we actually end up using on these problems over here. So this one has a radical, but the radical does not contain the trig function. Now it is a little bit easier, and you'll notice this one is already factored and it's already set up for zero factor theorem, so I don't have to worry about adding answers because it's already been factored for me. I didn't have to do any factoring on my own. This is just how the problem appears. So from here, I can use zero factor theorem, and I can say that tangent of x is probably going to be positive root 3, and sine of x is going to be negative 1. So then that brings me to the question, what angle can have this possibility where the sine would be negative 1 and the tangent would be root 3? So let's look at the unit circle and think about where sine is negative 1. So if sine is the y-axis, and I go around the circle, sine will be negative 1 at 270 degrees. Now, where is tangent the square root of 3? Two places, I believe. Let me think here. So this is going to be the 30, 60, 90 reference triangle. I should grab my unit circle. I'm just not sure what pile it's in right now. So the root 3 is going to be opposite of the 60. This will be 1, that'll be 2, that'll be 30. Okay, so if tangent is equal to root 3 and tangent is opposite over the adjacent, then this has got to be the tangent of 60 degrees. And if we look at our unit circle all students take, so the values of tangent being root 3 will be 60 degrees, and then add 180, and that would be 240 degrees. Okay, so what did they do to the sine? Oh, that's right. Okay, if you remember when we were doing our study on arctangent, we noticed that we can only use arctangent in the first two quadrants, right? Because if you do tangent expressions in trig, they don't really work past 180 degrees sometimes. So if we plug 270 into this original equation, it ends up not working because of the tangent identity. And the main reason is because if you were to do opposite over the adjacent, at 270, the coordinates on the unit circle are 0, negative 1. Opposite being like sine, and then adjacent being like cosine. We would have negative 1 over 0, and division by 0 is undefined, so we cannot have tangent at 270. So our two answers are 60 degrees and 240 degrees. I just saw that sign was missing. I was like, why? What did they do? Okay, last thing we're going to have is graphs of logarithmic functions. I should be able to do this in a minute. All right, so let's say they tell you to find the graph of, they want you to graph the following function. Y equals the log of 3.5 times y. Log base 3.5 times y. Now, the way that we're going to graph this is we're actually going to graph the function of the exponent and then do the inverse function for that. So what we would do here is we would solve this logarithm for y. So that's just going to take this up to that exponent. So 3.5 to the power of x is going to equal y, right? And we're going to graph this instead. All right, so this is an exponent thing. If we plug in, if we do our x and y table, if we plug in 0, then y is going to equal 1. 0, 1, that's 1 point right there. And then if we plug in, let's see here, 1, y would be 3.5. So at 1, we've got 3.5. And then if we plugged in -1, we'd have 1 over 3.5, which would be like smaller, like that. And then let's go ahead and plug in a 2 just for fun. 3.5 squared is going to be 11.5. So 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, and 0.5. Right. So this is the graph of our function. Like all exponential functions, it does a really large rise. Okay. Now you will notice this is not the graph of our logarithm. This is the graph of 3.5x equals y. Now the interesting thing about the graph of a logarithm is if we were to take the graph and cut it directly in half at a 45-degree angle, the graph of the logarithm makes the exact opposite arc. And it makes the exact opposite arc so much that we can take all of these points and switch them. So instead of making x 0, we would give it the y value, and y would be 0. So all I'm doing is I'm taking all these numbers and I'm flipping them. 3.5 for 1, 1 over 3.5 for -1, and then I forgot that was 11.5. 11.5 for 2. And we switch all these numbers, and then we're going to get the graph of the logarithm. So if I go to 1, 0, that is the first point. If I go to 3.5 and then 1, that is the second point. And then if I go to 11.5 and 2, that would be the third point. And then if I were to go to, where is the other one? Okay, -1. If I go to -1, then I'm going to get 1 over 3.5, right? Hold on. No, sorry. If I go 1 over 3.5, I get -1. Right. There we go. I was trying to do the x and y's normally. So if you graph your exponent function, and then you take all those x and y values, that'll give you the graph of the logarithm. And I forgot what this was. Yeah. So this is that graph. So this is the graph that we're looking for. This is the graph of the exponent. And if you're going to graph this, you don't even have to graph this exponent. You could leave it blank. You could just get the values for it once you solve the logarithm, reverse those values, and only graph the logarithm. You do not have to graph both of them. But you can if you want to. I won't take points off. That's it for this lesson. Sorry this video went a little long. If you have any questions, let me know on Moodle, and I will see you in class.